Hello! For my science fair, I chose to examine the efficiency of biofuels. As a result of the dwindling supply of non-renewable resources, I wanted to see if biofuels could be reasonable alternative sources of fuel for the future. I hypothesized that if the fuel with the highest energy density was burned, then the greater the heat transfer, which would result in hotter water temperature. Just as a little background, a carbon-neutral fuel has no net greenhouse gas emissions or a carbon footprint. Leftover material used to make biofuel can be used to feed animals. The United States Navy has even caught on to this idea. They built the Green Hornet, which runs on about 50% ethanol and can fly faster than the speed of sound. Biofuel can be generated from a variety of sources, primarily corn in the United States and sugarcane in Brazil. Biofuels can reduce greenhouse gas emissions by 13%. This experiment explores the heat transfer from fuel to the water according to thermodynamics principles and can be correlated to the energy transfer in a car from the fuel to the motor. Let's take a look at my experimental design. The independent variable throughout this experiment was the type of fuel used. I tested 4 fuels: gasoline, ethanol, motor oil, and vegetable oil. The control group throughout this experiment was the petroleum-based gasoline. I was able to use petroleum-based gasoline as a baseline to compare my other experimental groups to. The dependent variable throughout this experiment was the temperature of the water in degrees Celsius 1 minute after lighting the cotton ball. The constants throughout this experiment were the ring stand, amount of water in the can, the tap where the water came from, the outside air temperature, and the funnel used to put the water in the can. Let's take a look at my procedure. First, gather materials. Next, empty, clean, and prepare 10 soda cans. Pour 150 milliliters of fuel into a measuring cup. Then put a cotton ball into the fuel until it is completely soaked. With tongs, place 1 cotton ball into the holding can. Fill an empty soda can with 125 milliliters of tap water. Put the can on the ring stand over the can with the fuel. Put the thermometer into the foam to prevent it from touching the bottom of the can. Once you insert it into the can, record the initial temperature. Throughout my experiment, the initial temperature was 18 degrees Celsius. Then, light the cotton ball on fire with the lighter. Observe and record the temperature of the water 1 minute after lighting the cotton ball. Alternate which cans are used between each experiment so that each can start at room temperature. Finally, repeat steps 4 through 11 10 times for each of the 4 experimental groups. As you can see in this chart, I conducted 10 trials for each of the 4 experimental groups. From this data, I was able to calculate the average, median, mode, and range. In this graph below, you can see this data displayed on this chart in graph form. In the graph below that, you can see the final average temperature for each experiment. The red arrows on this graph signify the range and data points for each of the experimental groups. Here are the results. Gasoline had a 46.8 final average temperature. Motor oil, 27.2 degrees Celsius. Vegetable oil, 20.7 degrees Celsius. And ethanol, 75 degrees Celsius. Here are the energy densities for those 4 fuels. Ethanol, 26 megajoules per kilogram. Vegetable oil, 39 megajoules per kilogram. Motor oil, 44 megajoules per kilogram. And gasoline, 46 megajoules per kilogram. The energy densities for those 4 fuels are readily available online. Once I had conducted my trials, I wanted to see how much heat was really transferred. So I used the thermodynamics heat transfer equation displayed here. When using the thermodynamics heat transfer equation, you want to solve for Q. Q is the heat content in joules. To solve for Q, you take M, which is the mass of the water in grams, and you multiply that by C. C is the specific heat for the water. You multiply M and C by delta T, which is the change in temperature, so the final average temperature for whatever experimental group you're testing, minus the initial temperature of 18 degrees Celsius for all of my experimental groups. Here are the results. Gasoline, 15 kilojoules. Motor oil, 4.8 kilojoules. Vegetable oil, 1.4 kilojoules. And ethanol, 29.8 kilojoules. In conclusion, the one result that did not agree with the hypothesis was the increase in water temperature with ethanol, since it had the lowest energy density. I consulted Dr. Dan Chilcaz at Penn State University to see if he could offer any insight as to why ethanol in this experiment performed better than gasoline. Dr. Chilcott suggested that accumulation of soot outside the can containing gasoline indicates incomplete combustion. Soot is a sure sign of incomplete combustion, and as a result of this, all the energy released may not have been converted into heat. After the ethanol trials, very little soot was observed in the can, suggesting that its combustion was nearly complete. In this experiment, it was concluded that ethanol is an efficient alternative to petroleum-based gasoline due to its ability to produce heat. Vegetable oil, which produces significantly less heat, can still be used as a biofuel, but structural modifications, such as larger fuel lines, are needed for efficient use. The study confirmed that a biofuel such as ethanol could be a reliable, renewable source of energy. The environmental impact on relying on petroleum-based gasoline makes it a less desirable alternative because of the harm it can cause the environment. As part of future work, one would measure the weight of the cotton ball before and after burning to determine how much fuel is consumed and the theoretical energy release by multiplying the weight of the fuel burned by its energy density. This would be compared to the heat absorbed by the water, which would be calculated using the thermodynamics heat transfer equation. Thank you for your time and consideration.